Alright, just let us know when you start recording.
I've started.
2 seconds. Okay, so we're going to have a go at filling out page 169. For a number of you, you've found that quite a challenge. And so I might just do it with you for you to see if we can make that make sense. So I've connected to a force sensor and I've zeroed it in the vertical plane so that makes sense. What radius should I use? Well, this is a very short string. I might use 30 centimeters as my radius, so I put my bung there and I put my string to 30 centimeters, and then I grab a whiteboard pen and I put a line on my string. And so with my line on my string, I'll now know that my radius is 30 centimeters. So if I write r equals 30 centimeters, and can radius be 30 centimeters?
Yes.
Or should it be something else? 0.3
Oh, 3 meters.
meters. And then I'm going to need somebody who's going to be my lovely stopwatch measuring person who's going to measure
Go,
this with a stopwatch. Yep. Maybe we get a couple of you measuring this with a stopwatch, that'll be helpful. And so I create a loop and I put that over my force sensor. And how many times are you going to record for? 10. And so I'm going to grab over to my Fernet graphical analysis, and instead of 5 seconds, I'm going to put 20 seconds as the time it's going to time for. And then if I can get you, Maggie, to click collect when we're ready to go. And so I'm going to get it spinning right up at the point. And so we've got our stopwatches, people ready?
Collect.
And you hit collect. And so, should I say start? So we'll go and start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so who's got a time for 10 rotations?
4.48.
4.48. Any other times? 4.6. And so we could say that that's about 4.56 seconds. And so when we come over to our table, in here, we're going to write 4.56 seconds. And so what's the time for one rotation?
That divided by 10.
0.456. And if we go back to our graph, what's our force? It should have really been the same. And so if I care about this bit here, I can come over here and go view statistics. And it says it's got a mean of about 1.417. So we say 1.4 newtons was our hanging force. And then if I want to work out my velocity, I go 2 pi times the radius, which is 0.3, divided by the time period, which is 0.456. And that'll give me the centripetal velocity. And then I can check that if that's the right answer for the force. And so if I hit a calculator, we'll give you guys a race if you can do this in your calculators.
I don't know.
So
2 times pi times 0.3 is
2 pi times 0.3 divided by 0.456 gives you 4.1. Is that what you got?
Yep.
So 4.1 meters per second. And then the mass of my bung was, I don't actually know, 15 grams. So 15 over 1,000 times 4.1 divided by 0.3. And then that should give you the same number as what we measured over here, 4.17. Chuck this on the scales and it's 27.6 grams.
It's quite off.
And grams aren't kilograms, so 27.6 divided by 1,000 will make that kgs. I'm then going to times it by shift answer squared. That'll give me the top line equals divided by 0.3, 1.57. And 1.47, they're pretty close numbers, aren't they? They should be exactly the same. So in a sense, we've proved centripetal force by spinning a bung around our heads. So that's what we should have done. If you haven't got that in your books,
You can copy down my working so you have something to refer to.